Greetings, FQXI scholars. In the next 10 minutes of this video, I hope to convince you of one unambiguous point about the inherent geometry of quantum mechanics at the nuclear level. The argument is both simple and complex. Simple because it is ultimately just a matter of 3D geometry, but complex because it is a many-body problem. The argument is controversial in one respect only, and that is due to the fact that modern-day nuclear structure physicists are convinced that the nucleus is possibly a liquid, or possibly a gas, or possibly a probability cloud without internal structure. Their worldview is essentially that of mid-19th century chemistry before the advent of molecular structure. They had their formula, say C6H6 for benzene, and when Kekule suggested that it formed a hexagon, he was accused by the famous journal editor Kolbe of engaging in phantasmagorically frivolous puffery, now of course known as stereochemistry. Well, today you are in for the treat of nuclear-level phantasmagorically frivolous puffery, or what I call quantum nucleodynamics, or QND. So, good luck. Here is a unit cell of the face-centered cubic lattice that I will be talking about. The colored spheres represent nucleons, here yellow for protons and blue for neutrons, but colored in various ways in the slides that follow to represent various quantum features. Details of the lattice model and nuclear structure theory in general are available on the internet for free, and I encourage you to examine the relevant books and articles, software, and spreadsheets at your own pace to obtain a true understanding. Here is shown the origin of the coordinate system and all of the lattice sites near the origin. Fundamentally, a lattice means that the average position of each nucleon in any nucleus can be described by its lattice coordinates. The nucleons themselves are probably not colorful billiard balls, but for understanding nuclear structure, colorful geometry is useful. The lattice has a tetrahedron at its center, and the first four nucleons have x, y, z coordinates that are all positive or negative ones. In nuclear space, these values would be multiples of 0.716 Fermi to give the known nuclear density, but obviously it is easier to work with integers. Now, what is interesting is that using these integer coordinates, all of the quantum numbers of each and every nucleon in any nucleus can be calculated. Below is shown the lattice equation for computing the principal quantum number n. Clearly, the n value is a function of the distance of the nucleon from the center of the coordinate system. Plug these values into the equation and you get the correct sum. N equals 0 in this case. This is hardly rocket science, but I will show you that the same symmetry holds for all subsequent n shells in the lattice. Here is the n shell of the second energy level containing 12 additional nucleons. Using these combinations of positive and negative 1s and 3s, an n value of 1 is calculated. Here is the next n shell containing 24 additional nucleons in purple. Various combinations of positive and negative 1s, 3s, and 5s give n values of 2. The lower energy red and yellow shells are inside the purple shell. And here is the fourth principal energy shell containing 40 additional nucleons in green. Again, all coordinates are odd integers, and the closed shell is again triaxially symmetrical. Clearly, this is still nothing more than solid geometry, and I suspect that most of you are probably thinking that this entire story simply must be either trivial or somehow wrong. Well, that's not the case. Here are the first 7 n shells and their experimentally known nucleon occupancies, all built around a central tetrahedron. Significantly, all the other quantum numbers that are used to describe nuclear energy states can be similarly calculated in the lattice. Just as there are no 2 lattice sites with the same lattice coordinates, there are no 2 nucleons with all of the same quantum numbers. Each site is unique, as is each quantum state. The formula for all of the quantum numbers used in the Schrödinger equation are shown here. These include N, J, L, M, S, and I quantum numbers, as well as the nucleon's parity, which the textbooks tell us has no classical definition at all. One by one, these geometrical definitions of the quantum numbers are still little more than schoolboy geometry, but the total pattern should come as a shock, because the full set of quantum characteristics of each and every nucleon is dependent solely on its position in 3D space. Think about it. Quantum mechanics is notorious for being an abstract and abstruse, bizarrely incomprehensible world of mathematical formula that clearly work, but that are totally opaque to common sense understanding. And yet, at the nuclear level, quantum mechanics has a straightforward three-dimensional geometry. So what does this lattice representation of nuclear symmetries have to do with real nuclei? Let's start with the relatively simple case of the nitrogen-15 isotope. This is but one example from among thousands that are summarized in the Firestone table of isotopes. The horizontal line at the bottom indicates the nitrogen-15 nucleus in its stable ground state. It is a J equals 1/2 state with negative parity. Above it are shown the first 8 low-lying excited states at excitation energies between 5 and 9 MeV. On the far left are shown the experimentally measured spins and parities of these states. And on the right are shown the excitation energies and the lifetimes of these states before they decay to lower level energy states. In the middle are shown the transition probabilities of de-excitation to lower level states. The experimental data for this and some 2,000 other isotopes are wonderfully precise and clearly indicate the complexity of nuclear substructure. Unfortunately, the conventional understanding of nuclear structure ends at this juncture. But in light of the identity of the quantum symmetries in the Schrödinger equation and those in the lattice, each of these states has a unique 3D geometry. First of all, the ground state of nitrogen-15 can be shown as follows. With 8 neutrons filling the first 2 N shells, and 7 protons leaving one unfilled hole in the second N shell, the corresponding lattice structure for the ground state of this nucleus is unambiguous, and leads to the prediction that its J value should be 1/2 with negative parity, as is experimentally known. Moreover, there are equally unambiguous structures for each of the excited states for which spins, parities, and binding energies have been measured. Here they are for the first 8 low-lying excited states. In each case, the total spin and parity calculated from the lattice model are the same as the experimental values. In principle, the excitation energies can also be calculated, but that is a more advanced topic for another day. Let us examine the lowest lying excited state, a J equals 5/2 positive parity state. Precisely, those properties are obtained by moving the unpaired proton from its original position at coordinates 1, 1, -3 to a new site at coordinates 3, 3, 1. This is a J equals 5/2 state, colored blue, and a positive parity, colored green. We could spend the next hour going through the detailed geometry of each of these excited states, but the important point is simply that there are always lattice structures that correspond precisely with the quantum characteristics known from experiment. If a nuclear state can be described by the conventional Schrödinger equation, then there necessarily is a related lattice structure. In other words, there is a stereochemistry of nuclear physics, a unique geometry for each and every nuclear state. So there you have it. There is a geometry to the atomic nucleus. But ask any university professor who teaches nuclear structure theory about nuclear stereochemistry, and he will tell you that the lattice representation of the nucleus is wrong for so many reasons that he doesn't know where to start. He might even mumble something about phantasmagorically frivolous puffery. But I would suggest that the future of nuclear physics already belongs to those studying low-energy nuclear reactions in light of the geometry of quantum mechanics.